trying to learn this OBS studio so I can do proper videos like everybody else does on YouTube. Make it look cleaner and more professional. I should call Ben Davidson up. Maybe he can give me some tips. He's learning a similar program. Maybe he can help me out. Maybe. In the spirit of good cooperation. Anyway, folks, I'm trying to do better. I'll have to get back to that later. I just don't always have the time to learn new things, you know. Anyway, Brian here. It's Monday, October 6, 2025. I did this video yesterday, but I kept on running out of data on my phone and just a whole bunch of other problems. I had to splice everything together and put it into one big long video, so I have to start all over again. Tonight's talk, we're going to talk about the methodology of forecasting earthquakes. One particular one may be common. The other one is just something that I've been coming up with. So first, the statement that the sun triggers earthquake is not defined enough. It's not thorough enough, and it's not always true. The one thing to remember, it doesn't matter by whatever the delivery system or the what causes an earthquake. It is the highly energetic particles of the cosmic rays, consisting mostly of protons and some electrons, that do influence and trigger earthquakes, volcanic eruptions, and the rise of heat up through mantle plumes and hot spots. So a cosmic rays is the primary cosmic rays. However, when it reaches the Earth's atmosphere and reacts with Earth's nuclei, a reaction takes place where the creation of a secondary cosmic rays, showering effect, we call muons and others neutrons, but mostly muons, showering effect of muons which reach the Earth and penetrates through the Earth crust. If there is a magmatic body below, and if it's silica-rich magma, and if it's viscous enough, another process called bubble nucleation takes place, an expansion of the bubbles. It heats up the magma, it pressurizes it, and it rises. You will often see me do this. This is my representation of a mantle plume or a hot spot. So mantle plumes are anchored to the outer core where our magnetic field is generated from. All those highly energetic particles flow down through the magnetic cusps into the outer core. The magma is heated up, it's pressurized, it ascends up the mantle plumes. Consider my wrist being the transition zone, which is a transition between lower and upper mantle between 440 and 610 kilometers depth, approximately. When it comes to the underside of the lithosphere, in which the crust and the ocean sit upon, it creates what's called a mantle plume head. It can expand 1,000 or more kilometers in diameter, and I suspect that it has branches, arms, nodes, pushing up underneath the crust. This also brings up another term, not part of this talk, called lithospheric melting, melting of the underside of the lithosphere. It's a pressure. So if there's no volcanoes nearby, it's still putting pressure on the plates, earthquakes, and heat. Muons. So again, these particles consist of mostly protons and some electrons. And then when they reach the Earth's atmosphere, they interact with the atmospheric nuclei, and a change takes place, a showering effect of the secondary particles. Now, we can foresee earthquakes by two means or conditions. One, low pressure systems, and two, elevated geomagnetic instabilities from solar storms, if you want to put it in plain English. So one, from the impact of coronal mass ejections, which carries hundreds of billions of tons of the highly charged particles in magnetic field. And then as recently, from the faster solar wind speeds. So the average speed of the solar winds is anywhere from 250 to about 320 kilometers per second. That's average. But when a coronal hole openings up in the sun, it releases the faster solar winds, such as we've been experiencing recently. It is important to realize that. So a CME, when it hits us, the impact results can last for minutes to hours. A coronal hole stream accelerating the solar winds, carrying those highly energetic particles, can be a very long duration. It can be 24 hours, it can be 48 hours, it could be 72 hours long. A constant bombardment and pressure of the solar winds hitting our planet. And I'll show you some visual examples. Someone in the classroom, Arnold. Arnold is somebody who supports me. He's a flatlander. Flatlander is somebody who lives in Alberta. We're separated by the Great Rocky Mountain Divide. I'm on the other side, the better side, British Columbia. So, cosmic rays originate, so there's solar energetic particles that originate from the sun. But beyond the sun, there's what's called the galactic cosmic rays, which are 10 times more energetic than those that emit from the sun. So this is why I say, people say vaguely, oh, the sun triggers earthquakes. Not always. Not always. Galactic cosmic rays, the remnants from supernova, for example. So let's get into some videos. In this animation here, this is planet Earth. This is the magnetic field, the magnetosphere, which protects the Earth, mostly, from the stream of solar particles, and in this case, coming from the sun. But they also originate from the galaxy as well. Now here we have a NASA animation of the solar winds. So planet Earth, obviously, surrounded by its protective magnetic field, magnetosphere. Magnetopause, which is the side that is taken in the solar particles, the sun-facing side. So let's just play the video. For the most part, the magnetosphere is deflecting the solar particles and then entering in through the polar magnetic cusps. Now pause it for a minute. So I say normally. So if we have a dipole, only two magnetic poles, normally, magnetic north, magnetic cusp, south, south cusp. Normally, highly energetic particles will be funneled down the cusp, through the cusp, into Earth's interior. Then sometimes you'll have an interaction with the magnetic field of the solar winds, or CMEs, and Earth's magnetic field. Now the cosmic rays, when a cosmic ray reaches Earth's atmosphere, it interacts with the atmospheric atoms where a secondary showering particle takes place with the creation of muons, such as in this example. So cosmic ray enters Earth's atmosphere, interacts with the atmospheric nuclei, creating a secondary cosmic showers of muons. So this is the magnetopause model from the Australian Bureau of Meteorology. Planet Earth, light blue is the sun-facing side. The orbiting satellites, the magnetopause, or the outer edge of the magnetosphere, sun over here, solar winds. So I'm just going to play this model here. This is for today. So this is the solar winds compression onto the magnetic field. Nominal right here, 350, 370 kilometers per second. It does increase to about 400 plus. Has not affected the satellites. A couple of times it comes close. So let's go back to the geomagnetic storm. That's September 30. I don't think that was it. Let's try the first. Okay, here we go. So now we're getting up to over 700 kilometers per second. Compressing on our magnetic field, pushing in closer to the Earth. Let's go to the next day. So next we have what's called the KP index, the planetary K index. I call it quite simply a measure of the irritability on our protective magnetic field. Right now our conditions are very low. Once we get into KP5, then we reach geomagnetic storm conditions, 6, 7, 8, and so on. Now the NOAA website, they do it at 3-hour increments. I don't use that one. This one here measures it at 30-minute increments. So when we get a spike in these bars, reaching geomagnetic storm conditions, G1 minor, G2 moderate, G3 strong, and so on. Once we have that timing established, you've seen me use this, then I'll find out which side of the planet, the day side, is going to be receiving the brunt of either the CME impact carrying the highly charged particles in magnetic field or the accelerated solar winds. I'll enter the times, the dates. So as it's been demonstrated several times recently, our recent dayside impacts have started Papua New Guinea, working their way to Indian Ocean. The suggestions has been for increased activity, Java Sea region. And of course, most of the times they do happen. So that's pretty much it for this segment. Forecasting or suggesting seismic responses as well as volcanic eruptions. Following, let's just say, anywhere from a 24-hour to 72-hour or even more window after geomagnetic impacts. For example, in 2023, there were 24 magnitude 7 and above earthquakes. 75% of those happened within 72 hours following geomagnetic storms. So that's one method of forecasting or suggesting where an earthquake may happen. Now we're going to get into the more complex method of forecasting earthquakes by low pressure systems. Now, tracking low pressure systems is not only to predict changes in weather, but also increases the probability of earthquakes, volcanic eruptions, and the rise of heat after the track of low pressure systems, be it thunderstorms through the Midwest, hurricanes, typhoons, cyclones. The main thing is the drop in the barometric pressure. This takes a heck of a lot of study. I'm going to try and keep it as simple as I can. Okay, this is for Arnold in class. If you're still awake, if you haven't fallen asleep yet, Arnold. So an open umbrella represents a high pressure system. The rain droplets, try and imagine these being the secondary charged particles, the muons, being absorbed by the high pressure system or otherwise deflecting. from the area directly below. If this umbrella closes in on itself, that would represent a low pressure system, allowing increased muon penetration, saturation through the crust. You happy, Arnold? I may have some overlapping segments on this video, so repeating myself, because I have to splice everything together. So once again, tracking low pressure systems not only helps to forecast changes in weather, but also increases the probability of seismic and volcanic responses, as it has been so demonstrated with a high degree of accuracy. So once again, it's the penetration of the muons under certain atmospheric conditions of low barometric pressure and low atmospheric temperatures. There's chapters and chapters and chapters of this information. I try to keep it as simplified as I can. How I came about this method of prediction was studying how scientists use muons to measure structures within inside volcanoes, volcanic chambers, to structures inside the pyramids. But they found that they had to recalibrate the muon detectors for variable counts of muons because of alterations in the atmospheric conditions. So I sort of reversed what they did to come up with my own little theory model. So again, they had to take into account the increase of muon counts based on atmospheric conditions. So with pressure systems, with high pressure system, there is more mass to absorb the secondary cosmic rays, muons, lessening the amount reaching the surface. This is also called the absorption effect. So this is high pressure. As atmospheric molecules heat up and expand, more muons decay before they reach the surface due to the increased muon propagation paths, resulting in a decrease in muon intensity on ground level. So high pressure provides some protection. The opposite happens when there is a low pressure, low barometric pressure systems, results in increased muon counts reaching and penetrating the Earth's surface. Then we also have what's called the temperature effect. So the atmospheric temperature plays a role as well in the amount of muons reaching the surface. Temperature effects influence the creation and disintegration process of muons in the atmosphere. So muons generally show a minimum in summertime and a maximum in the wintertime. It's also called seasonal temperature variations. So low barometric pressure, low atmospheric temperature results in an increase in muon counts. Another visualization is the umbrella. An open umbrella represents a high pressure system, deflecting or absorbing those muons, providing an area of protection directly below the zenith. If the umbrella closes, now we have the increased showering particles reaching the Earth. Zenith angle is the angle between the point of location and the zenith, or the point directly overhead, or in this case below the umbrella. The zenith is the axis perpendicular toward the horizontal plane. Horizontal plane, perpendicular. High pressure. So from all this, we can forecast or suggest, as I say, seismic responses, volcanic eruptions, and the rise of heat after the passing of thunderstorms, hurricanes, typhoons, cyclones. And again, as has been so demonstrated so many times. It depends on what, if any, magmatic structure there is below that low pressure system track. Any volcanic areas, magmatic bodies, subduction zones, other fracture zones, and so on. So that's the second method for how I use to suggest seismic responses following these low pressure systems. The problem is going to be, folks, is because the ongoing geomagnetic excursion, the weakening of the protective magnetic field, which also destabilizes and weakens our jet streams, which creates an increase in low pressure systems all over the place. That, along with, as I suspected, the development of the beginning phases of a multiple magnetic pole field, just complicates the thing. So it can actually give you a headache sometimes trying to put it all together and do a forecast suggestion where these events may happen. So I just wanted to show you how I come about to forecasting earthquakes. I may have gotten some of these segments a little bit mixed up. I'm going to put it all together right now, see what it looks like, and then send it off to you. That was all, as you were.